Hold a 1-inch tungsten cube. It weighs nearly 1 pound, denser than gold, heavier than lead. Drop it and the floor dents, not the cube. This metal refuses to melt until 6,192 degrees, hotter than Earth's core beyond temperature where other metals vaporize. Light bulb filaments, armor-piercing bullets, rocket nozzles, tungsten survives conditions that destroy everything else. Yet it starts as dull gray rock, looking worthless. How does brittle ore transform into metal that won't surrender? Why does one nation control 70% of global supply? Stay with us. You'll witness industrial-scale mining reshaping mountains and discover tungsten's shocking secret. This indestructible metal is so brittle in pure form it shatters like glass. The Dayu tungsten mine in Jiangxi, China dominates the landscape. An open pit 3 miles across descending 800 feet into earth. Giant haul trucks, each carrying 400 tons, crawl spiral roads looking like toys from rim's edge. This single mine produces 40,000 tons of tungsten concentrate annually, enough to manufacture 2 billion light bulbs. 70% of world's tungsten comes from Chinese operations like this. Watch the blast sequence. Drillers bore holes 50 feet deep in geometric patterns across the pit floor. Each hole gets packed with explosives, 200 pounds per hole, hundreds of holes per blast. The detonation ripples across the face in sequence, fracturing 10,000 tons of rock in 30 seconds. Dust clouds billow 300 feet high, visible from orbit. What took nature millions of years to create, humans demolish in half a minute. The ore, wolframite and scheelite, contains just 0.5% tungsten. That means 99.5% is waste requiring removal. Massive crushers reduce boulders to gravel. Ball mills grind further. Rotating drums containing steel balls pulverize ore to powder finer than flour. The grinding noise is deafening, continuous thunder as metal crushes rock. Separation uses gravity and magnetism. Wolframite, being dense and magnetic, concentrates easily. Scheelite requires froth flotation. Chemicals make tungsten minerals hydrophobic, clinging to bubbles while waste sinks. The concentrate, now 15% tungsten, ships to processing plants. China's dominance isn't accidental. They control reserves, processing knowledge, and critically tolerate environmental damage Western nations won't accept. Tailings ponds stretch miles, filled with chemical-laced sludge that'll remain toxic for centuries. Processing concentrate into pure tungsten trioxide requires acid digestion. The concentrate gets dissolved in hydrochloric or nitric acid, violent chemical attack breaking molecular bonds. Tungsten dissolves while impurities precipitate out. The solution, now containing tungsten compounds, undergoes pH adjustment causing yellow tungsten trioxide powder to crystallize. This powder undergoes hydrogen reduction, the crucial transformation. Inside tube furnaces heated to 1,800 degrees, hydrogen gas flows over tungsten trioxide. The hydrogen strips oxygen atoms, leaving metallic tungsten powder. But here's the challenge. Pure tungsten powder is useless. The particles don't bond. Press them together and they crumble. Tungsten's ultra-high melting point makes conventional melting impossible. No crucible survives temperatures required. The solution? Powder metallurgy. Powder metallurgy bypasses melting through sintering. Particles fuse below melting point under pressure and heat. Tungsten powder gets pressed into desired shapes using hydraulic presses, generating 50,000 psi. The compacts, called green bodies, are fragile, handle roughly, and they disintegrate. The green bodies enter sintering furnaces operating at 4,500 degrees in hydrogen atmosphere. At these temperatures, tungsten atoms migrate across particle surfaces, welding together without liquefying. The process takes 12 hours. What emerges has transformed. The powder compact becomes solid metal with 99% density. Dimensional changes are predictable but significant. Parts shrink 18% during sintering. Engineers must design oversized greens compensating for this shrinkage. Pure tungsten remains problematic. It's brittle at room temperature, difficult to machine. The solution? Alloying. Adding 2% thorium or lanthanum dramatically improves workability. These elements prevent grain growth during sintering, creating fine-grained structure that machines more easily. The most common tungsten product worldwide is tungsten carbide, tungsten powder mixed with carbon, sintered together. Tungsten carbide achieves hardness second only to diamond. Cutting tools made from tungsten carbide last 10 times longer than steel equivalents. Mining drill bits, machining inserts, industrial dies, anywhere extreme wear occurs, tungsten carbide dominates. The material cuts steel like butter but shatters under impact. Drop tungsten carbide block on concrete and it explodes into fragments. The combination of extreme hardness and extreme brittleness defines tungsten's paradox. Wire drawing demonstrates tungsten's remarkable properties. The sintered tungsten gets heated to 3,000 degrees and drawn through progressively smaller diamond dies. The wire diameter reduces from 1/4 inch to thousandths of an inch, thinner than human hair for light bulb filaments. This drawing process work hardens tungsten, increasing strength. Modern LED lights made tungsten obsolete for household illumination, but specialty applications remain. Electron microscopes, X-ray tubes, high-temperature furnace elements. Anywhere electricity must flow through extreme heat, tungsten wire delivers. The element's resistance increases with temperature, making it self-regulating. In light bulbs, hot filament resists current flow, limiting power draw and preventing burnout from voltage spikes. That wire glowing white-hot at 6,000 degrees, tungsten operating at 70% of its melting point, yet lasting thousands of hours. Military applications drive demand relentlessly. Tungsten's density, 19.3 grams per cubic centimeter, nearly identical to gold, makes it ideal for kinetic penetrators. Armor-piercing ammunition uses tungsten or tungsten alloy cores. Fired from tank cannons at 5,000 feet per second, these projectiles punch through steel armor through sheer mass and velocity, not explosive force. The ethical controversy is intense. Depleted uranium performs similarly but raises radioactivity concerns. Tungsten offers equivalent performance without radiation, but mining's environmental cost is staggering. Each ton of tungsten requires processing 200 tons of ore, generating mountains of toxic waste. The metal that survives Earth's most extreme conditions is extracted through processes poisoning the planet. Swedish chemist Carl Scheele identified tungsten oxide in 1781, studying the mineral scheelite. Spanish brothers Juan and Fausto El Huyar isolated metallic tungsten 2 years later. The name derives from Swedish Tungsten, heavy stone. For a century, tungsten remained laboratory curiosity. Everything changed when Thomas Edison needed light bulb filaments in 1879. He initially used carbon, which burned out quickly. By 1904, manufacturers switched to tungsten, revolutionizing electric lighting. World War I revealed tungsten's military value. High-speed steel cutting tools containing tungsten enabled mass production of weapons. Today's annual production exceeds 90,000 tons, with China dominating supply chains so completely that Western nations consider tungsten a strategic vulnerability. Carbon emissions remain problematic as tungsten production generates 8 tons of CO2 per ton of metal, primarily from energy-intensive processing. Recycling exists but remains limited. Only 30% of tungsten gets recycled, far below rates for aluminum or steel. Here's the secret we promised. Tungsten's incredible strength comes from its weakness. Pure tungsten is brittle, shattering easily. But that brittleness stems from its crystal structure. Atoms packed so tightly that dislocation movement, the mechanism allowing metals to deform, essentially stops. This atomic rigidity creates the highest melting point, extreme hardness, and resistance to deformation. The metal survives temperatures melting steel because its atoms simply refuse to move. Adding trace elements creates enough flexibility for workability while maintaining strength. From Chinese mountains to cutting edges worldwide, the transformation completes. We've mastered metal that defies conventional metallurgy, processing it through techniques developed when melting proved impossible. That drill bit cutting through rock, that filament glowing white-hot, that bullet-piercing armor, all share tungsten's fundamental contradiction. The strongest metal is also the most fragile. The element that won't melt is useless without powder metallurgy. We've learned to work with nature's extremes by accepting, not fighting, inherent limitations. Tungsten doesn't compromise. Neither do the engineers who've learned to shape it.
Every year, hundreds of power units, bridges, and turbines are built worldwide. But there's one component almost nobody knows exists. How can a piece of metal over 50 feet in diameter be stronger than any welded structure? Why is it forged without a single seam, as if grown from a solid ingot? And how did this technology, created for nuclear reactors, suddenly start transforming wind energy, hydroelectric plants, and even the global heavy forgings market? Stick around till the end. I'll reveal the main secret of this giant ring that even many engineers don't know about.
To really get a sense of the scale here, picture a soccer field. The goal is over 23 feet wide. This ring's diameter, more than double that. You could easily fit multi-story buildings inside it, or a plane. And it's all one solid piece of stainless steel, not a single weld anywhere. In the past, rings this size were made by welding together several large segments. Looked good, but those longitudinal seams always carried a hidden risk. Any micro crack, any welder's mistake, and during an earthquake or under long-term loads, that seam could become the weak point. Chinese metallurgists decided to go a different route. Don't glue it together, grow the ring from a single piece. They used a technique they call additive forging. Here's how it works. Instead of trying to stretch a billet to the right size all at once, they forge it repeatedly in layers, gradually building up and rolling out the metal in the shape of a giant ring. Think of it like rolling out dough and folding it into a log multiple times to make it thick, even, and free of air pockets. Here, instead of dough, it's heated stainless steel and presses exerting thousands of tons of force. First, they melt exceptionally high-grade steel with nickel, chromium, and molybdenum. These additives provide strength, ductility, and corrosion resistance, even in radioactive and high-temperature environments. The resulting ingot looks like a massive metal barrel. It's heated in furnaces where temperatures are many times higher than in a kitchen oven, then transferred to presses. The blank is first flattened, then pierced through, then rolled in a circle, each time rotating and hammering it so the structure becomes as uniform as possible. The incremental forging technique means the metal is constantly built up in the needed direction, while simultaneously being compacted, driving out voids and defects.
With each pass through the press, the ring grows in diameter, but its walls maintain the required thickness, and the steel's grain structure aligns. Engineers constantly monitor temperature, compression force, and deformation rate. If the metal cools too much, it becomes brittle and can crack. If it overheats, the structure flows and the steel loses strength. So the entire operation is run like a complex recipe. Precise steps, holding times, checks at every stage. In the end, you have a solid ring without a single seam. This is critical for a nuclear reactor. The support flange acts like a belt, holding together the vessel walls and all the internal guts, the reactor core, heat exchangers, internal structures. It bears not only 7,000 tons of weight, but also thermal deformations, vibrations, and possible seismic shocks.
Picture the reactor as a massive pressure cooker. This ring? It's the belt that can't budge, not even a micron. No weld seams means way less risk of cracks under cyclic loads, and it makes the whole thing tougher against earthquakes. Of course, forging isn't the end of the story. The ring goes through heat treatment, heated and cooled on a precise schedule to lock in the steel's key properties: yield strength, impact toughness,
resistance to creep at high temps. Then come the endless checks, ultrasonic testing for hidden flaws, mechanical tests on samples sliced from machining allowances, hardness measurements around the whole perimeter. Only when engineers are confident the metal behaves identically at every single point does the part get cleared for duty in a nuclear unit.
What's really fascinating is that the breakthrough with this record-breaking ring didn't stay trapped in the nuclear club. The same idea of forging massive solid hoops started spreading to other industries. The hydro turbines at large hydroelectric plants have enormous ring-shaped components that hold the runners and guide vanes. Wind turbine towers need powerful flanges that transfer loads from the blades through the nacelle to the steel column. The fewer welds in these critical parts, the better they handle vibrations and tough operating conditions. Additive forging technology makes it possible to produce large-diameter, solid rings for them that last longer and perform more reliably. The world's most powerful open-die forging presses, including those at China's China Erzong, reach 80,000 tons of force and can deform ingots weighing anywhere from several dozen to over 250 tons, which is exactly what opens the door to forging rings on this scale.
On a global scale, large-scale forgings for the energy sector come from a tight circle of suppliers. Facilities in Japan, China, France, and Russia, each with its own production lines for large reactors, generators, and turbine rotors. Demand for seamless rings isn't just growing in nuclear power. The forged flange market for wind turbines was valued at roughly $1.5 billion in 2023 and could hit around $3 billion by 2032, with seamless ring forgings claiming a significant chunk of that pie. Offshore wind farms need massive flanges and rings that can handle punishing wind loads, salt water, and constant fatigue cycling. Here, seamless rings have a clear edge over welded ones, thanks to lower cracking and deformation risks.
Similar rings show up in hydropower too. Turbine bands, guide vanes, massive flanges for high-pressure pipelines. Anywhere a failed weld could spell disaster, manufacturers switch to giant one-piece forgings. The story of that Chinese ring over 50 feet across, that's just the tip of the iceberg for the entire heavy forging industry. It shows just how far modern blacksmithing has come. Diameters over 50 feet, weights north of 330,000 pounds, design nodes in the thousands of tons, and service lives measured in decades without replacement. And market data for power forgings and wind flanges hints that we'll see more and more of these record-breaking rings in nuclear, hydro, and wind energy every year.
More than half of Earth's entire weight is iron, 32% of the planet's mass. Earth's core is a gigantic ball of molten iron the size of the moon. But iron rules on the surface too. Every second, humanity produces 60 tons of steel, 2 billion tons per year. That's more than all other metals combined. 95% of all metal used by civilization is iron and steel. Without iron, there'd be no skyscrapers, bridges, ships, cars, or trains. How do fiery rivers of molten metal at 3,600 degrees emerge from red ore in city-sized quarries? You'll see explosions in quarries, blast furnaces as tall as 30-story buildings, converters where oxygen turns pig iron into steel in minutes, and rolling mills where 1,000-ton slabs get rolled into paper-thin sheets. Watch to the end. The finale shows why iron holds the world together. This is the story of the metal that built civilization. The Lebedensky quarry in Russia is one of the planet's largest iron ore quarries. Depth, nearly 2,000 feet. Width, 3 miles. From the edge, you can't see the bottom. A gigantic wound in the earth from which 100,000 tons of iron ore are extracted daily. Excavators as tall as 10-story buildings scoop rock with buckets holding 1,800 cubic feet. One bucket is like a small house. Dump trucks with 360-ton capacity haul ore up the spiral road. Wheels taller than a person. But before loading the ore, it needs to be blasted. Drilling rigs create holes 65 feet deep. Tons of ammonium nitrate explosive are packed into these holes. The explosion? Earth trembles. A wall of rock tall as a skyscraper crashes down. A dust cloud rises 3,000 feet. After the dust settles, excavators begin work. The ore is reddish-brown, sometimes almost black. Magnetite and hematite, iron oxides. Iron content ranges from 30 to 60%. The rest is waste rock. The ore goes to a processing plant. Massive cone crushers grind bus-sized chunks. The noise can be heard for miles. Ore gets crushed to fist size, then to gravel, then smaller. It enters ball mills, steel drums 20 feet in diameter, 33 feet long. Inside are hundreds of tons of steel balls. The drum rotates, balls drop, grinding ore into fine powder. After 8 hours of grinding, you get reddish-brown dust. It's mixed with water, creating pulp, liquid slurry. This slurry passes through magnetic separators. Magnetite sticks to magnetic drums. Waste rock washes away. The concentrate contains 65 to 70% iron. From this, they make pellets, granules the size of walnuts. Wet concentrate gets rolled into balls on special drums, then fired at 2,400 degrees Fahrenheit. Pellets harden, becoming rock solid. These pellets are raw material for blast furnaces. Each plant produces millions of tons of pellets yearly. They're loaded onto trains and shipped to steel mills. A blast furnace is a steel tower 330 feet tall, 46 feet in diameter. 30 stories of pure metal and fire. Lined inside with 3-foot-thick fireproof brick. Internal volume, 176,000 cubic feet. Iron ore pellets, coke, and fluxes like limestone or dolomite are loaded from the top, in layers, like a layered cake. Several hundred tons at a time. From below, through tuyères, openings in the walls, hot air is blown in. Air temperature, 2,200 degrees Fahrenheit. Pressure, 4 atmospheres. Coke ignites. Temperature in the furnace's lower section reaches 3,600 degrees Fahrenheit. Pellets slowly descend, heating up. Different reactions occur at different heights. First, moisture leaves the ore. Then, at 930 degrees, iron oxide reduction begins. Carbon from coke strips away oxygen. At 1800 degrees, ore becomes spongy iron. At 2700 degrees, iron melts. Drops of molten metal flow down. At the furnace bottom, molten pig iron accumulates, an iron alloy with 4% carbon. Pig iron temperature at the furnace bottom is 2,700 degrees Fahrenheit. It glows blindingly white with an orange tint. Pig iron is denser than slag, so it stays at the bottom. Slag, molten impurities and fluxes, floats on top. Every 4 hours, they open the tap hole, an opening in the furnace's sidewall. Pig iron tapping is a fire show. A stream of molten metal flows down channels. Sparks fly dozens of feet. The brightness requires dark glasses to watch. Pig iron flows into massive ladles on railroad cars. One ladle holds 300 tons. It's a locomotive made of molten metal. The ladle gets covered to prevent cooling and shipped to the steelmaking shop. One blast furnace operates continuously for years. Stopping is catastrophic. Metal would solidify inside. The furnace produces 10,000 tons of pig iron daily. That's like 100 railroad cars. Major steel mills have 10 to 15 blast furnaces. But pig iron isn't steel yet. It's brittle due to high carbon content. Steel is needed, an alloy with less than 2% carbon. Pig iron gets poured into a converter, a massive pear-shaped vessel 33 feet tall, lined with fireproof brick. It holds 350 tons of molten metal. The converter tilts, pig iron pours in, steel scrap is added for cooling. The converter returns to vertical position. An oxygen lance, a tube 20 inches in diameter, lowers from above. Oxygen flow begins. A jet of pure oxygen at 150 pounds per square inch pressure strikes the molten metal. Violent reaction begins. Oxygen oxidizes carbon, silicon, manganese, impurities in pig iron. These exothermic reactions release enormous heat. Temperature rockets to 3,200 degrees Fahrenheit. Metal boils and churns. Flame tongues several feet high shoot from the converter mouth. Sparks and molten drops fly everywhere. The blowing process takes 20 minutes. In this time, 350 tons of pig iron become steel. Carbon burns down to 1% or less. The converter tilts, steel pours into a ladle. The molten metal glows blindingly white at 2,900 degrees Fahrenheit. Alloying elements get added to the ladle: manganese, chromium, nickel, molybdenum, depending on the steel grade needed. They mix it by blowing argon through. Then steel gets cast. There are two methods. First, continuous casting. Molten metal pours into a crystallizer, a water-cooled copper mold. Below, a solidifying blank emerges, a slab 8 inches thick, 6.5 feet wide. It glows red, surface temperature around 1,800 degrees Fahrenheit. Gas cutters slice the slab into 33-foot lengths. One slab weighs 25 tons. Second method, casting into ingot molds. Steel forms. This creates ingots up to 50 tons. These ingots and slabs are semi-finished products. They go to rolling mills. There begins the final transformation, turning thick blanks into thin sheets, rails, or beams. Slabs heat in reheating furnaces to 2,200 degrees Fahrenheit, red hot. Then they go to the rolling mill. It's a line of dozens of rolls, steel cylinders 3 feet in diameter weighing dozens of tons. Rolls rotate toward each other. The red-hot slab enters between rolls. They squeeze and roll it. The slab gets thinner and longer. It passes through the next pair of rolls, even thinner, dozens of times. An 8-inch thick slab becomes a sheet 1 to 2 millimeters thick. Length grows from 33 feet to over half a mile. Rolling speed on finishing mills reaches 50 miles per hour. Red-hot steel ribbon flies through the mill, sparks flying everywhere. Temperature drops to 1,400 degrees Fahrenheit, metal darkens. The strip cools with water, winds into giant coils weighing 20 to 30 tons. This is hot-rolled steel, the foundation for car bodies, appliance housings, building structures. Global steel production is 2 billion tons yearly. China produces over 1 billion tons, half the world's output. India, Japan, the US, Russia are other major producers. Steel is infrastructure's backbone. 95% of metal structures are steel, from skyscrapers to tin cans, from tankers to paper clips. Iron and steel are civilization's skeleton. Iron is the oldest metal after copper and bronze. The Iron Age began 3,000 years ago. First, iron came from meteorites, ready-made metal fallen from the sky. Egyptian pharaoh Tutankhamun was buried with a meteorite iron dagger. Smelting iron from ore was learned by Hittites in Asia Minor around 1200 BC. They kept the secret for centuries, but technology spread. Iron weapons were stronger than bronze. Iron plows worked soil better than wooden ones. Civilizations with iron defeated civilizations without iron. Medieval times, iron was made in small furnaces. The Industrial Revolution began with blast furnace invention in the 18th century. Early furnaces used charcoal. Later, they switched to coke from coal. The 19th century brought the converter process, rapid pig iron to steel conversion. Bessemer, Martin, Thomas, names that changed the world. The 20th century was steel century. Skyscrapers, bridges, ships, automobiles. Without steel, there'd be no modern world. And so, traveling from explosions in 2,000-foot-deep quarries through giant crushers and magnetic separators, through 300-foot-tall blast furnaces at 3,600 degrees and converters where oxygen burns out carbon in 20 minutes, through rolling mills where 8-inch slabs become millimeter-thin sheets, steel emerges, the metal that built civilization. 2 billion tons per year. 60 tons every second. The metal everything around us is made from. Every skyscraper, every bridge, every car, every ship. It's iron, mined from red ore, remelted in fire, rolled into sheets. More than half of Earth's weight is iron. The planet's core is molten metal. And on the surface, iron rules. 95% of all metal is iron and steel. From nails to bridges, from paper clips to skyscrapers, iron holds the world together. Without iron, humanity would collapse back to the Stone Age. No machines, no electricity, no internet. Everything's built on iron. From fiery rivers of molten pig iron in blast furnaces to steel beams holding up skyscrapers, iron is the foundation, the base, civilization's skeleton. Metal of the gods that became metal of the masses. The most abundant, most important, most irreplaceable. Iron, the metal that holds the planet together.
Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this. More than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called tuyeres. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit, dense as lead but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high, temperatures hitting 3,200 degrees, create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steel making requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this: alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised. Every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.
Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or culm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer green skin and inner nodes, leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water, or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Jiangxi scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family. Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home. Imagine a metal that's lighter than steel, stronger than aluminium, and can withstand temperatures at which other materials simply burn up. A metal used to build aircraft that conquer space and implants that serve people for a lifetime. Sounds like science fiction? But this is titanium, one of the most mysterious metals on Earth. It starts with tiny grains of ilmenite and rutile and ends up as parts for supersonic jets and spacecraft. But few people know, behind the gleam of titanium lies a manufacturing secret so dangerous and energy intensive that it's rarely spoken of. If you watch till the end, you'll learn something that will forever change your perception of this metal. The story of titanium production begins in the late 18th century when, in 1791, a British clergyman and amateur mineralogist named William Gregor discovered a new metal in the mineral ilmenite, which is now the main source of titanium. Initially, this metal was called menaconite, but later, in 1795, the German chemist Martin Klaproth rediscovered the element in the mineral rutile and named it titanium, in honor of the mythical Titans, giants of ancient Greek mythology. However, the pure metal was first successfully isolated only in 1825 by the Swedish chemist Berzelius, though at that time it was contaminated with impurities and practically unsuitable for industrial use. The first attempts at industrial production of titanium began only in the 20th century. In 1910, the American chemist Matthew Hunter obtained a small amount of pure titanium, and the real breakthrough came in 1925 when Dutch scientists Van Arkel and de Boer developed a method for producing high-purity titanium, paving the way for its widespread application. From the mid-20th century, titanium production developed intensively, especially in the USA, where the metal became indispensable in aviation, the space industry, and military applications. The production of titanium starts with the mining of titanium-bearing raw materials, mainly the minerals ilmenite and rutile, which contain titanium oxides. These ores are found in placer or lode deposits and are widespread across the globe, particularly in Australia, Canada, China, Norway, and South Africa. After mining, the ore undergoes a complex multi-stage processing. First, it is enriched, separating the titanium minerals from the waste rock to obtain ilmenite or rutile concentrates. Then, the concentrates are subjected to chlorination, which results in the formation of titanium tetrachloride, a volatile substance that is purified by distillation. This process allows for the removal of impurities and the production of a high-purity intermediate product. Next, the titanium tetrachloride is reduced with magnesium or sodium in special reactors at high temperatures in an inert atmosphere, producing titanium sponge, a porous metallic powder. This titanium sponge is then pressed, melted, and cast to obtain ingots or billets for further processing. The production of titanium is energy-intensive and expensive due to the complexity of the technological processes and the need to work in high-purity conditions. The main industrial method for producing titanium is the Kroll process, which remains the global standard. It involves the chlorination of titanium ore, purification of titanium tetrachloride, and its reduction with a metal, allowing for the production of high-quality metal for aviation, space technology, medicine, and other industries. Thus, titanium production begins with the mining of ilmenite and rutile, goes through complex chemical reactions and physical processing to transform natural minerals into a high-tech metal that combines lightness, strength, and corrosion resistance. The initial stages of titanium production are based on a complex, multi-step technological process that begins with the extraction and preparation of titanium-bearing raw materials, mainly ilmenite and rutile. These minerals contain titanium oxides, which must be converted into chemically pure titanium tetrachloride. To do this, the titanium ore concentrates are chlorinated in fluidized bed reactors at a temperature of 1,800 degrees Fahrenheit, where carbon and chlorine gas react with the raw material to form titanium and carbon monoxide. This tetrachloride contains impurities of other metals, which are removed by distillation to obtain high-purity technical titanium. The next key stage is the reduction of titanium tetrachloride to metallic titanium. The most common industrial method is the Kroll process, in which titanium tetrachloride reacts with magnesium in a vacuum chamber at high temperature. The result is titanium sponge, a porous metallic powder containing impurities of magnesium and magnesium chlorides. This reaction mass is subjected to vacuum distillation to remove impurities, after which the titanium sponge is pressed and remelted into solid ingots or slabs. The resulting titanium ingots are then used to produce alloys, rolled products, sheets, and complex parts. The entire process requires strict control of purity, temperature regimes, and safety, as titanium actively reacts with oxygen and nitrogen when heated. Just look at how incredible it is. A porous, light, and seemingly fluffy mass of metal. This is titanium sponge. It looks nothing like a regular metal bar, but more like a piece of metallic sponge or foam, only made of titanium. But this fluffy material is the first step towards creating strong and reliable titanium ingots, which are then used in aviation, medicine, and other high-tech industries. First and foremost, titanium ingots can be used to create titanium alloys, mixtures of titanium with other metals that enhance its properties. To obtain an alloy, alloying elements are added to the molten titanium, most often aluminium, vanadium, molybdenum, iron, or niobium. These additives change the metal's structure, increasing its strength, heat resistance, corrosion resistance, and improving its workability. The production of alloys usually takes place in vacuum arc furnaces, where the metal is melted at high temperatures in a protective atmosphere to avoid oxidation. To achieve a homogeneous composition, the alloy is remelted several times, after which it is cooled and prepared for further processing. The next stage is rolling. Ingots or slabs of titanium and titanium alloys are heated to a certain temperature to make the metal more malleable and are passed through special rollers. Rolling allows for reducing the metal's thickness, giving it the desired shape and size, as well as improving its structure and mechanical properties. The result is various types of rolled products: strips, ribbons, wire, and bars. Rolling can be hot or cold, depending on the requirements for the final product. From these rolled products, sheet metal is made, thin, flat blanks that are widely used in construction, aviation, medicine, and other industries. Titanium sheets are distinguished by their high strength and corrosion resistance, and are also easily subjected to further processing, cutting, bending, and stamping. The production of sheets requires precise control of thickness and surface quality, so after rolling, they are often subjected to additional processing, such as polishing or anodizing. To create complex parts, various methods of processing titanium and its alloys are used. These can include mechanical milling, turning, grinding, as well as modern technologies such as additive manufacturing using laser powder bed fusion. Additive technologies allow for the creation of parts with complex geometries that are impossible to produce with traditional methods. This is especially important for the aviation and medical industries, where lightweight, strong, and precise components are required. Furthermore, to enhance their performance characteristics, titanium products can undergo heat treatment, annealing, quenching, or aging. These processes change the internal structure of the metal, improving its strength, hardness, and fatigue resistance. In aviation, titanium is used for 15% of the weight of a modern passenger aircraft, significantly reducing its overall weight and increasing fuel efficiency. In the medical field, about 70% of implants, such as artificial joints and dental prostheses, are made from titanium or its alloys due to their biocompatibility and durability. Every year, millions of tons of chemicals are produced worldwide, but one of them, chlorine, is truly staggering in scale. In the United States, over 12 million tons of this gas are made annually. That's the same weight as 120 Gerald R. Ford aircraft carriers, the heaviest ships in the world. But where does this dangerous, yet vital substance come from? It all starts not in a lab, but in underground deposits of common salt. From there, it involves electricity, membranes, and an entire industry that consumes more power than entire American states. And if you watch till the end, you'll discover the secret that chlorine hides behind its sharp smell. The United States is one of the world's largest producers of chlorine. Each year, plants in the country produce over 12 million tons of the gas. This number is just hard to wrap your head around. Imagine the weight of the aircraft carrier, the Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 of those aircraft carriers weigh. This enormous quantity makes chlorine one of the top 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is common rock salt, or sodium chloride. But it doesn't arrive at the plant in salt shakers. It's either mined in the form of huge chunks, or, far more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, creating a saturated salt solution called brine. And it's this concentrated, salty as tears solution that is our raw material. But it's still impure. It's full of contaminants, calcium, magnesium, and other minerals that can clog up our expensive equipment. So before the main show begins, the brine goes through a thorough purification process. It's passed through a whole series of tanks where chemicals are used to precipitate and filter out all the impurities. What comes out is a perfectly clean, clear, and very salty solution, ready for the main event, electrolysis. Now, let's head to the heart of the plant, the so-called cell room. This is a huge loud hall filled with rows of strange enclosed tanks connected by a network of pipes and thick electrical cables. These are the electrolyzers, or cells. This is where all the magic, or more accurately, all the chemistry will happen. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure salt solution is poured. And into this solution, two electrodes are submerged, a positively charged anode and a negatively charged cathode. Now, a direct electric current of colossal power is applied to these electrodes. And this is where the split begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions. The electric field forces them to move. The positive sodium ions are drawn, as if by a magnet, to the negative cathode, and the negative chloride ions to the positive anode. And it's at the anode that the whole point of the process occurs. Each chloride ion that sticks to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately pair up, forming a molecule of chlorine gas. Billions of these molecules gather, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, it takes about 2,500 kilowatt hours of electricity. Now, multiply that by 12 million tons a year. It turns out that this industry consumes about 30 billion kilowatt hours annually. That's more than the annual electricity consumption of entire states, like Vermont or Wyoming. It's like an entire city of 1 million people, working year-round just to split salt molecules. But what's happening at the cathode? The sodium ions have drifted over there. But they don't turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. That's our first byproduct. And the hydroxide ions left in the solution combine with our sodium ions to form sodium hydroxide, or caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We've just created three substances: chlorine, hydrogen, and caustic soda, and they must never be allowed to mix. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react to form bleach, which is not what we want at all. So, the genius of the technology lies in separating these three products at the very moment of their birth. This is done using special membranes or diaphragms. Imagine a thin, paper-like, but very clever partition standing between the anode and the cathode. This membrane, made of a special polymer, is like a bouncer at a nightclub. It allows the positive sodium ions to pass through to the cathode, but blocks the negative chloride ions, preventing them from getting into the cathode space. This way, chlorine is born and collected in one part of the cell, while hydrogen and caustic soda are in another. Now we need to collect our harvest. The moist, hot, greenish-yellow gas is continuously pumped out of the anode chamber. First, it needs to be cooled. It's passed through heat exchangers where it gives off its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. So, the wet chlorine is passed through towers where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cool, but still gaseous chlorine is ready for the next stage: liquefaction. It's compressed under enormous pressure and cooled at the same time. Under this double whammy, the gas turns into a clear, amber-yellow liquid that looks like oil. This liquid chlorine is much easier to transport and store. It's poured into special thick-walled steel tankers, or rail cars. Every step of this process is carried out under completely sealed conditions, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we've produced is collected, purified, and used either as fuel for the plant itself, or sold for ammonia production, or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. It's one of the most important products in the chemical industry, used to make soap, paper, aluminium, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, we learn to obtain three extremely important substances at once, which form the foundation for thousands of other products that surround us in our daily lives. Now let's see where all this enormous amount of chlorine goes. You might think it all goes into disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So where does the other 95% go? It's a key building block for other products. About 40% of all chlorine goes into the production of this universal plastic. The vinyl windows in your house, water pipes, medical IV drips, vinyl records, the credit card in your wallet, all of these were born thanks to chlorine. Another 40% or so is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. Chlorine is also a key component for bleaching paper, giving it that clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that American industry produces over 13 million tons of this vital alkali annually. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other can rise, allowing plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy. From the plastic pipes under our streets to the medicines in our pharmacies.